Sorry, everyone, give me 1 second to try to figure this out. If whoever is doing number 2 wants to go first, that'll give me some time to try to connect.
Yeah, I can go first. Let me share my screen. Okay. All right, can everyone see it and hear me? Okay, awesome. So I'm going to be going over question 2 from problem set 5. And so basically the question is asking, or it gives you the information, your system is in a frictionless piston, which is isolated, and no heat transfer will occur with the surroundings. And then it gives you a chemical reaction where 1 mole of A is turning into 2 moles of B and giving off 50 joules of energy. And it tells you that you can assume that B is an ideal gas. So starting off with kind of like the important things to note about this question is the first one, which is the most important, is that it's isolated. So there's going to be no heat transfer. This will be important like for the questions asked. Also, it's a frictionless piston. And B is an ideal gas, so ideal gas rules will apply to it, which will be useful for solving later questions. So the first question is just asking if A can be considered an ideal gas. And so there's like one kind of critical piece of information that will give you the answers to that. But first, let's talk about just like what an ideal gas is. So an ideal gas is monatomic, and it consists of atoms that do not interact with each other. And so the interatomic interactions are very weak, and you can just neglect them for like the purpose of like solving problems in like this class. And so there's like one key piece of information that can tell you what whether or not A can be an ideal gas. Does anyone know what it is or care to guess?
Would it be the fact that the 2B is twice the moles of A?
Yeah, exactly. So you know that B is an ideal gas, and you know that 1 mole of A is going to form 2 moles of B. So you know that A can't be an ideal gas because that means that it's a compound molecule because it's breaking up sort of into smaller pieces. And so you know that A can't be an ideal gas. Yeah, that's perfect. And then question 2 is saying the piston is not allowed to expand, so there's no change in volume. So it's giving you an additional piece of information about the problem, and then it's asking what the change in energy of the system will be. So when the energy of a system changes, which is what like this question is asking, it can change in one or both of 2 ways. And so the first way is that the system releases heat to the surroundings, and then the second is that the system does work on the surroundings. So and this equation, you can find like a derivation in the textbook, but it's a pretty important equation. It's just the change in energy is going to equal the work done plus, which is W, plus the heat transferred, which is CQ. And so in this problem, like I mentioned before, it states that there's no heat transfer with the surroundings. So from that, you automatically know that dQ or Q heat is going to equal 0. And it also states that there's no change in volume in this like subsection of the question. And that means that there's no work done. So dW is also going to equal 0. So if you just kind of fill out the equation using this information, you'll find that the change in energy is also 0. And so yeah, there's no change in energy of the system. And then for question 3, it says, after the reaction is complete, the piston is allowed to expand against a constant external pressure of 1 atm until the volume is doubled. The initial volume is 1 liter. What is the change in energy of the system containing B molecules only? That's why it's important to remember that B is an ideal gas. So like for questions like these, we can use like ideal gas information laws. And then remember to put your answer in joules. So now we know that the system like is doing work on the surroundings. So we kind of need to redefine the variables that we used for the last problem. They're not like true anymore for this portion of the problem. So what we want to know is what the heat transfer is going to equal, what the work will equal, and ultimately what the change in energy will equal. And so just to start off, still the same. There's still no heat transfer with surroundings. And so Q will still be 0. And energy is what we're trying to solve for. So we don't know what that is. And then the work is going to be equal to the external pressure times delta V, which is the change in volume. And so we have this new equation, which is, this is just the old equation, that du equals Q plus W, but now it's also equivalent to negative P external times delta V. And so at that point, this becomes just more of like a simple math problem. So you know that the external pressure is 1 atm. Oh, and you know you can use this equation because it says it's at a constant external pressure. And delta V is going to be 1 liter because the initial volume is 1 liter and then the volume was doubled. So 2 liters minus 1 is 1, change in volume. And then just like an important note, you're going to want to convert to joules because it asks for the answer in joules. And so 1 Pascal meter cubed is equal to 1 joule. So you want your units in the form of Pascal, which is pressure, meters cubed, which is volume. And so to convert, you can convert ATM by multiplying it by 1.01 times 10 to the 5th, and that'll give you pascals. And liters, which is what volume is in, times 10 to the negative 3rd will give you meters cubed. And then another thing is that's important to remember is you want to know like what sign your work is going to be, because that'll like change depending on how the work is being done. And so remember that if the system is doing work on the surroundings, then the term will be negative. So you can like kind of add in like that term afterwards if that's how you like to think about it. And then for the last portion of this question, which is just what is the change in temperature of the system? So one thing that we can consider first is kind of just so like a sanity check basically is, will the change in temperature be positive or negative? Like will the temperature increase or decrease? And if the energy of the system is decreasing, then like that temperature will be decreasing. So our final answer for change should have a negative sign based on like the information from the previous questions. And then what equation should we use? And we need to remember that B is an ideal gas. So now we can use like, also that's all like that will be left in the system. And so we can use ideal gas laws to figure this out. And so for an ideal gas, the energy, the total energy is going to be the same as the kinetic energy because there are no interatomic interactions. And kinetic energy has the equation of 3/2 nRT. So U will also equal 3/2 nRT. And then you just isolate for temperature because that's a variable trying to find out. And then U will be the answer that you got from last question in joules. And then N is 2 moles because this, and R will be 8.3145 joules per mole Kelvin. And if you want like a more in-depth derivation of how you get the kinetic energy of an ideal gas, there's like a box in the book that's like a pretty good resource for that. It goes like pretty in depth of why that is. And I think that's it for this question. Does anyone have any questions?
Yeah, for part 3, do we have to take into account the 50 joules?
For part, let me just go back. That's the one about the person's one. That's not really relevant
Wouldn't we have to add the 50 joules to the work done? Or
I think like the 50 joules of energy like given off is still sort of within, that's like what is causing the piston to expand, I'm pretty sure. If any other tutors like have an idea about that. But I guess like it's not really, if like that energy is within the system, it won't be like, for instance, like, because sorry, we're going to 2, but in 2, it's like this isn't a change in energy. The system is still in the same energy. Like this 50 joules of energy is offsetting the loss in potential energy that you have from like A being turned into B. So that's not changing the energy of the system. It's just like offsetting the, it's like kinetic energy that's offsetting the change in potential energy.
I have a question for part 4.
Mhm.
So when it asks for the change in temperature, is it only considering the process in part 3?
Yes.
Oh, okay. Makes a lot more sense.
All right, I'm gonna try to see if this works now. Okay, cool. So you're given that you have a piston with n equals 3 moles, and then 3 moles, and then it expands isothermally. So at a temperature that stays constant at 300 Kelvin, and then the volume increases from 1 to 2 during the expansion. So what you want to do first is to identify how you define internal energy, and that would be given by the potential internal energy U is equal to the potential energy of the system plus the kinetic energy of the system. And then that translates over to the change in internal energy by just putting a delta in front of all of these. And then what you want to notice is that for ideal gas, the potential energy will be 0 because ideal gases do not interact, nor do they store energy in their bonds. So that goes to 0. And then kinetic energy is given by 3/2 nR delta T. And then we're given that this is an isothermal reaction. So delta T would be 0, and therefore kinetic energy is 0. So this entire thing would be 0. And then how much heat is transformed to the system during this process. So there's another equation for the change in internal energy. You could either use this equation that I gave above, or there's also du equals dq plus dw, where dq is equal to heat transfer, and then dw is equal to work. And then recall from part A that du is equal to 0. So rearranging this equation, we get dq is equal to the minus dw. And then we know a formula for the change in work for an isothermal reaction, and that would be negative nRT natural log of V2 over V1. And then you just plug things in, the negatives cancel out. So you're left with 3 moles times RT is 2.5 kilojoules per mole. And then natural log of 2 over 1. And then that should give you 5.19 kilojoules. And notice that you're not left with moles. However, the question says to give it into the units of kilojoules per mole. So you're given, so this is the amount of energy transfer to the system for 3 moles. So to get per mole, you just divide this by 3 moles because we have 3 moles, and then you're left with 1.73 kilojoules per mole.
Isn't
So-
ln of? Oh, sorry, never mind.
Okay. So the gas in the system is heated, so the temperature rises, so it's not isothermal anymore. And then, but now the volume is constant. So since the temperature rose, that means the internal energy of our system changed. So if we just write our equation again, du plus dq equals dq plus dw. And then what we could cancel out here is that since work is a function of volume, and since volume is constant, that means work goes to 0. So we're given du equals dq. And then from part A, we know that du is a function of kinetic energy, which is 3/2 nr delta t. So 3/2 equals dq. And then you just plug in everything that you know. So you have 3/2, 3 moles, r, and then delta T would be 15 Kelvin. And then that should give you dq. And then the last part says that instead of an ideal gas, you now have an organic compound. So what you want to keep in mind is that organic compounds are now real molecules. They're not ideal anymore. So now everything changes somewhat. So potential energy is not 0 anymore because real molecules can store energy and interact with each other. So it's not 0. And then, however, kinetic energy is still 0 because isothermal reaction. So what you're left with is that the change in internal energy is equal to only the change in potential energy. So you could state that this increase in energy is because of an increase in potential energy. Oops. And that's because real molecules can interact with each other, store energies in their bonds as rotational energy and vibrational energy. So if we have a molecule like this, it could store energy vibrationally, or it could do rotational. So that's how energy is stored, and that's why energy increases. And then let me check if there's any questions. So why do we divide by 3? So this answer, 5.19, is only in kilojoules. However, the question says give it in kilojoules per mole. So 5.19 kilojoules is for 3 moles of gas. So to get per mole, you divide by 3 because we have 3 moles of gas in our system. All right.
Do you mind just showing the rest of part C really quickly? Sorry, I missed it.
Sorry, of what?
It's okay, don't worry.
No, it's okay. Which part? Part C?
Yeah, part C.
Okay, 1 second.
Thank you.
No problem.
All right, I'll go ahead and share my screen for question 3. Okay, so for question 3, for part A, we're given 2 molecular systems, each of which contain, 2 energy distributions for a molecular system, each of which contains 3 energy levels, and for which the energy distances between each energy level are the same. And you're asked to find which of these distributions corresponds to a Boltzmann distribution. So since we're given the number of molecules in each level, we might want to start with what a Boltzmann distribution says about the number of molecules you can expect to find at each energy level. So recall that, for a Boltzmann distribution, you have that the number of molecules at each energy level is proportional to e to the negative ui over kBt, where ui is just the energy of the energy level. So in particular, then, you know that for any two energy levels, the ratio of molecules you can expect to find from one to the other is equal to e to the negative delta u over kBt, where delta u is just the difference between the energies of the two energy levels. And you can just find that by dividing this by the energy level, the same expression for energy level I minus 1. And the important thing to notice about this is that if this distance is constant for every single change in energy level across the distribution, as is the case here, then this value is a constant. In other words, for the Boltzmann distribution, we can expect the ratio of the number of molecules we find at each energy level to be roughly the same. So essentially, how you would find whether which of these distributions corresponds to the Boltzmann distribution is you would take the ratio n2 to n1 and n3 to n2 for each of these two distributions, and whichever of these two distributions preserves the ratio to within a reasonable margin of error is going to be your Boltzmann distribution. And then for part B, ignore this 2 over here. You're given the potential energy levels for two systems, which are shown here. And you're told that these are due to conformational transitions only, but translational motion and vibrations, the energy levels are the same between these two, so they're not shown. So remember, changes in potential energy can be due to the conformational transitions for these protein molecules, as well as for translational motion and vibrations. But again, the only major difference between these two systems is for the conformational transitions. And you're asked to find which of these systems has a higher heat capacity. So to think about this, let's start with considering what change in potential energy for either of these systems would look like. And remember that we know that delta U corresponds to the change in potential energy plus the change in kinetic energy from question 1. And since we know that the only thing changing the energy of the system right now is the heat flowing in, since we're just considering heat capacity, we can just set this equal to delta Q. And what we can get from this is that for a given input of heat energy, that's going to correspond to a given change in potential energy as determined by these potential energy levels and a given change in kinetic energy. And we know that heat capacity corresponds most directly to a change in kinetic energy, since a lower heat capacity means that for a given input of energy, the temperature of the system goes up faster. So if we consider these two energy level diagrams, the biggest difference that I want to point your attention to is the distance for the first energy gap. So we know that for system B, for example, this gap is relatively small between the first few energy levels. So if heat flows into system B, it's much more likely that molecules will begin to start populating these higher energy levels, and system B will start to gain potential energy as a result of that. Whereas for system A, this huge gap makes that much less likely. In other words, potential energy for system A gains less quickly, and thus as a consequence, the same amount of heat, more of that energy will go into kinetic energy. In other words, for a given input of heat energy, more of that energy goes towards kinetic energy or temperature for system A. And then based on that, you should be able to determine which of these two systems has a higher heat capacity. Are there any questions for that?
I have a question.
Yeah, sure.
If the heat is high enough, then couldn't the system reach that higher energy level in A? Like, because it seems like if the heat is high enough, then A would have a higher heat capacity because it can store more potential energy at like the 8 kBt level than B could.
I don't know that it could necessarily store more potential energy overall, since we see more energy levels spread out across B anyways. But I would say that for the purposes of this, the the first energy gap matters the most, since we're always going to have some distribution of molecules across these. There's that first energy level gap is always going to have some effect due to the molecules that stay present at that first energy level. Does that make sense?
Okay.
Could you explain why that big gap means that more energy would go to the kinetic energy and not the potential energy?
Right, yeah. So again, going back to this equation, for a given input of heat, and let's assume this is just some constant number, since we're talking about heat capacity, we want this per unit of heat input. That energy is divided off between potential energy and kinetic energy in terms of how it changes the energy of the system. So for system A, we note that the gap here is extremely large compared to the same gap for system B. So this gap essentially corresponds to the probability of having a certain number of molecules transition from this energy level to this energy level. So for a given input of energy, it's much less likely in system A that that energy is going to aid a given group of molecules to start populating higher energy levels. Whereas for system B, that's much easier to do. So if that energy then can't go towards changing the potential energy of the system, since molecules aren't populating the higher energy levels as much, that energy has to go towards the kinetic energy, since that's the only other place left for it to go. Does that make sense?
Okay, yeah, that makes sense. Thank you.
Okay, then I will start doing question 4. Question 4 is an exercise on how to do the actual calculations for the Boltzmann distribution. For part A, you're given these two situations, but we're only looking at the first situation in figure A, where you have 3 molecules in different levels, and you want to see the probability of finding these of seeing molecule 3 compared to seeing molecule 1 in those different levels. So we should remember that the probability of finding a molecule in any energy level will be equal to some constant times e to the negative EI over kBT. But since we're taking the relative probabilities, we don't actually have to care about this constant. This constant will be divided out when you take PI over, say, like PJ. So now we will just take the energies for for molecule 3 and molecule 1 and plug them in. And you'll have that P3 over P1 will then equal e to the negative E3 over kBT over e to the negative E1 over kBT. This can be rewritten as e to the negative change in energy over kBT, which should be a familiar equation. And look at the figure, you should be able to see that this change in E would be 3 kBT, since molecule 3 is at 3 kBT and molecule 1 is at 0. And you should be able to calculate that and find an actual value. For part B, you're asked for the probability of situation A and the probability of situation B, where you're considering all 3 molecules for situation A and all 3 molecules for situation B. So similarly, since we're dealing with 3 molecules in each situation, we don't actually have to worry about the constant, since the constant will cancel out for each corresponding molecule. So we can just instead write them as relative probabilities. And here, since we're really we don't yet have a relative benchmark to look from, we always look at the energy difference from ground when looking at relative probabilities, because the ground state is where we expect to find the lowest energy of molecules that molecules can be in. And for this situation, the ground state is 0 kBT. So this makes our calculations very easy, because we don't have to really consider a non-zero ground state, and we can just almost directly plug in our energies into the probability into the Boltzmann equation. So for situation A, since all the particles are independent, we will just multiply their probabilities together of finding them in these different energy levels, which would be negative E1 over kpt for A, and then so on E. Yeah, and for part B, for situation B, it would be a similar thing where you have E negative 1 over kpt and so on, where E1 would be the energy of particle 1 in situation A, E2 would be the energy of particle 2 in situation A, and so on. And you should be able to cancel out the kBTs in the exponents and find that you will eventually get a answer that is e to the something, and that will give you your answer for part B. And that should be all for question 4.
All right, let me get started on question 5. All right, can you guys? I can't see the comments, so I'm going to take that as a yes. Cool. Oops, let me delete all this. All right, so for question 5, we are given like basically a protein binding scenario. We have a protein that binds to a drug, and we're measuring the heat capacity under different scenarios. Graph A is without the drug, and graph B is with the drug. So that's just a quick recap of the question. So part A is asking, explain why the heat capacity goes up and then goes down. So specifically in graph A, so like this region right here. I guess I could start with writing down some useful equations. So we have dH dt is equal to the specific heat. And then that means that the integral of, if we do separation of variables and get the integral, we'll know that that h is the integral of this curve right here, curve A. So basically what that's telling us is that we need energy to unfold the protein. Before we can start, we need energy to unfold the protein. And then while we're melting the protein or unfolding the protein, we have this spike, where it gets easier and easier to, since this is a derivative curve, it gets easier and easier to unfold the protein until it reaches this inflection point, and then it gets harder and harder to unfold more of the protein. And this region is where we're melting. Cool. All right, so part 2 is asks, what's the significance of the temperature at which the heat capacity has maximum value in graph A? So that's this point right here. So like I said, as you increase the temperature, it gets easier and easier to unfold protein, and then it gets harder after this inflection point. So if we take the integral of this curve, we get something that looks like that with about 0.5, and this is the proportion unfolded being that inflection point. That's and the proportion at which 50% of the protein is unfolded is the melting temperature. So this inflection point is the melting temperature, melting point of the protein. All right. So now we're moving onto graph B, and it's asking what the purpose of this peak right here is. So there's 2 interactions that we're dealing with here. We're dealing with the protein interacting with itself when it's unfolding, and then also the drug protein interaction. So from part A, we know that this peak right here corresponds to the protein-protein interaction. So we can just use process of elimination to figure out that the smaller peak is the drug protein peak. And specifically, since we're increasing the temperature, the drug is dissociating from the protein. All right, cool. Now we're getting a little bit more in part 5. We're going to get to use this equation finally right here. So I'll just copy it down there. And we're asked if we can basically estimate the change in enthalpy when the drug binds to the protein. So we start with this equation, and we can do some calculus on this. So we use separation of variables, d equals Cp dt, integrate both sides, and we get h of t is equal to the integral of Cp dt, specific heat with respect to time. And then we can use the fundamental theorem of calculus, to get h from T1, sum T1 to T2 is equal to the integral from T1 to T2 of the specific heat. All right, cool. So this is how you would do it. And then, you could plug in your values for T1 and T2. That's supposed to be 1 down there. And you'd be able to calculate that. All right, so part 5 finally asks us to do some calculation. And it's basically, part B asks us to do some calculation. And basically we have a 10-liter ideal gas at 300 Kelvin, and it expands to 30 liters under 1 atm of pressure. And now we want to we want to calculate the work. So I'll do that first. So basically we know that the work is equal to the pressure times the change in volume. And we can just plug in our numbers here. We know the pressure was 1 atm, and the change in volume was 30 minus 20, or 30 minus 10 equals 20. So we have 20 atm liters of work. So now we can use our conversion factor of 101.325. Sorry, what is this? Joules per atm liter. And we get some J joules of work. Maybe I should use a different variable, X joules of work. All right, so now we can use this to pretty easily calculate the amount of time that this light bulb can stay lit. So we can start by writing the fact that power is equal to, which is in units of watts, is equal to joules per time. So we have our power. This is 25. And we have our joules, which we got up here. So I'll just put that in X. And we're solving for time. So we can rearrange this and we get the time it can stay on is X joules over 25. X joules over 25 watts. And that's our answer for the time. All right. And that should be it for question 5.
For the, when you were solving work, why is it not negative?
Sorry, for which question? Which part?
For 5B. 5B, the first part, it's when you solved for work, isn't work negative P delta V?
Negative P delta V. Oh, we're calculating, yeah, so it depends on what you're calculating for here. The question itself says calculate the work done by the gas. Since the gas is putting energy into the system because it's causing the system to expand from 10 liters to 30 liters, the work done by the gas is positive, and the work done on the system is negative. Does that make sense? So if we were calculating the work done by this, or work done on the system, you'd be right, but we're actually calculating for the opposite thing here.
Okay, that makes sense. Thank you.
Oh, also for the person who said, isn't Cp the derivative with respect to time, or temperature, not time? If I said time, I'm sorry, I meant temperature. But yeah, it is a derivative with respect to temperature. Cool.